Okay, in previous videos, I talked about how to sketch a root locus by hand, and I went through all 6 rules, and that included, I think, 2 different examples. This video is going to be yet another example, a complete example using at least 5 of the rules. By the way, here's a formula sheet that came out of all that. This is what I let my students use on exams and for homework. And you can find it on my website, which should be down in the comments or the description of the video. So here's the formulas. Keep this handy. And for this example in this video and some future examples, they're all going to be based on this configuration, where G and H are already monic. They have monic numerators and denominators. And this K is the parameter of interest. So computing the L of S is simple in this case. It's the product of G and H. So here's the example. There's the G, there's the H. Oh. Well, first, this little guy has complex roots. So we can either use the complete to square method, find out that its poles are at -1, or its roots are at -1 plus or minus J3, or you could use the quadratic formula. But anyway, between the product, we have a pole at 0, pole at -8, and then this complex pair of poles, -1 plus or minus J3. That is 4 poles. And there's only one 0, and it is at -2. So N is 4, M is 1, and minus M is 3. So at this point, we know we're going to have 4 branches of root locus, where the 4 poles of the closed loop system are going to be as K goes from 0 to infinity. The root locus will have 3 asymptotes, meaning 3 branches go off to infinity. Another branch goes into this 0 and -2. So step 0 was just put these guys, put the poles and zeros of L on your chart, on your complex plane chart. Here I'm using increments of 2. So here's the pole at 0. Here's the guys at -1 plus or minus J3. Here's the pole at -8, and here's the 0 at -2. Okay. Thinking ahead, where is the root locus on the real line? Coming from the left, 0, encountering 0, counting 1, ignore the complex. So it's on the real line between this pole and that 0, then not here because I have 2 guys to the right. And at this point, I have 3 guys to the right, so on the real line left of this pole. Here we go. What's next? The asymptotes. I have 4 poles, 1, 0, N minus M is 3. Go back to that formula sheet. N minus M is 3. So here's where the asymptotes are going to go. Here's how you calculate where the center is. I'm not going to go through all that again, but it's on the formula sheet. That's what it's going to look like. And where does it hit? Where is this middle on the real line? There's the formula. It's at -8/3. Over 2, not quite 3. Now the next thing is departure angles. Let's just go through. How about this pole? Well, you can ignore every pole on the real line to its left, and you can ignore complex poles because it's on the real line. Or ignore everything except the -180 degrees in the formula. This guy's going to depart going strictly left. What about this 0? The angle from this pole, 180 degrees. From this is 0. These guys cancel, so I have 180 plus the 180 from the formula, that's 360, 0. Is an arrival angle of 0, which means take a little line, an angle of 0, which is about to the right, which means the branch is going to go in along that line, into this 0 along that line. So you can kind of see you're going to get the branch just going from this pole into that 0. This guy, let's see, pole and 0 on the real line cancel, complex poles cancel. So I just get a minus 180. So this guy starts out going left. That's the asymptote. He's just going to keep on going left. So the only hard ones are, well, this upper angle, and then this one will just be the mirror image. So let's see, go through angle from the 0, I'll call that 70 degrees. Using a formula from the formula. Now I need the angles from the other 3 poles. I'll say this guy is 120, this guy is exactly 90, and I'll say this guy is 20. Put that in the formula, subtract the 180 as the formula says. I get 20 degrees by eyeball. If I did it exactly with the calculator, I would have got 30 degrees. Out of this branch, it starts out going a little bit, mostly right and a little bit up. Kind of going towards the right half plane, and it's eventually going to catch up with this asymptote, right? This guy's going to do the mirror image down to the right and left. We could draw a root locus at this point. Here's what I did, doing it by hand. Here's what MATLAB did. We need to know exactly where these guys cross the imaginary axis. We need to use rule 5. And that is where the root locus itself crosses the asymptotes. So don't use this rule to draw the asymptotes. It's where the actual root locus branch goes through. And for that rule 5, we had to go through the pain of Ruth Hurwitz, coming up with the characteristic equation. Here's what K L of S is. I have to multiply this denominator out, getting to this point. Then the characteristic equation is this denominator plus this numerator. Still have to combine terms. Finally, here is characteristic equation of the whole closed loop system. Ruth, it's up to 4th power. I'm going to have 5 rows in the Ruth array, 4S3 down to S0. First row is going to be 1, 26, 2K. Second row is going to be 10, 80 plus K, 0. Continue doing the Ruth's array, and the algebra gets a little screwy to find this term. This, and let's see, we're looking for where can you get 0 in this left column. If I just make K equal 180, I get a 0 here, but I get a non-zero term here. Find where it is on the imaginary axis. We're looking for a row of all zeros. So if this A is 0, we get a row of all zeros. Here's the A. When is it 0? You got to put it over a common denominator, use a quadratic formula. You get answers of minus 180 and 8 for K. But we're only looking at K greater than 0. K equals 80. You get this guy equals 0 and a row of all zeros. You go back to our Ruth Hurwitz stuff and use the auxiliary equation. So if I put 80 up here, I get 100 over 10. I get 10 s squared plus 2 times 80, 160. Okay, there's the auxiliary equation. which means my omega is this 160 over 10 or 16. My omega squared is 16, which means omega is 4. Sorry for my little bump down there. That means that's exactly where the root locus crosses the imaginary axis, right at J4 and minus J4.